Okay, this is the third lecture in the series on the COVID-19 pandemic, and in this one we're going to look at some mathematical predictions of how the pandemic is likely to progress in the future based on how it progressed in the past. Now, it's a really good idea to have a good read on this article here, so click on the link on the original PowerPoint slides, a really good summary of what happened in Wuhan in February, March and April. The predictions in there were pretty much correct. And then much of the data that I've been accessing is using this site called Worldometers, and this will give you case numbers for every country in the world, and it's updated on a daily basis. So in this session we're going to look at data that has been published, and we're going to critically analyse this data. So that means really putting it into context and not just believing the raw figures as being a true representative of what's really going on. So we're going to analyse this data like a scientist would, not how the general public would necessarily look at this data. And the key point of this session is to show what case numbers were probably like in March 2020, just before lockdown, and the effects of lockdown, because that doesn't reflect what is seen in the official figures. So this table just shows how pandemics emerge, and if you've got an infectious agent with an R0 of 3, as we saw last week, and if on average one infected person passes that infection on to 3 other people in 5 days, then you can make some crude estimates as to how many people are likely to be infected 5, 10, 15, 20 up to day 35 later. And they are fairly crude estimates because pandemics don't quite work this nicely, but what you can see is all you're doing is multiplying by 1 times 3 after 5 days, multiply by 3 again, and on day 10 there are 9 new cases, and just repeat the process. And what you can see is early on a pandemic could actually go relatively unhidden, and then suddenly it rears up with thousands and thousands of people affected, and that number can increase very, very quickly in a very short period of time, which is effectively what happened back in February and March. So what I've done is I've taken that data from the previous slide and plotted it assuming a doubling time of every 4 days or every 3 days. And what you can see is that these two graphs follow exactly the same shape. Okay? Because we've got a linear axis here. However, the difference between these two graphs is the scale. Here we've got up to about 2,000 cases by day 35. Here we've got up to 16,000 cases by day 35. So the shape of the graph is identical, they look identical, it's only when you look at the scale you see the difference. And this is where we use log graphs, or use the log to base 10 axis on the graphs. And what if this effectively does is gives equal spacing from 1 to 10, from 10 to 100, and from 100 to 1000. Because from 1 to 10 is a 10-fold increase, and from 10 to 100 is a 10-fold increase. And these two sets of data have been plotted on a log graph, and they both give a perfect straight line, because both graphs are showing a doubling time of, this one is 4 days, so that increases more slowly. This one has a doubling time of 3 days, so this one increases more quickly. The rate of increase is exactly the same for each of these two data sets. They appear to have the same shape, but the axis is different, and this graph here shows that both graphs are increasing at a constant rate. And these graphs are really important because the slope of this graph tells us the rate of the increase within of our pandemic. So if this is a steep straight line, then we know that the pandemic is increasing very quickly. If it's shallower, it's increasing less quickly, and that's more obvious to see than on these graphs here. Okay, so this is UK death data from the start of the pandemic through to August, plotted either on a linear graph, as you can see there, and a log graph, as you can see there. And these are taken straight from the Worldometers site. And you can see that the two graphs are showing the same data, but they look completely different. Now on the linear graph, because there was a huge increase in deaths throughout August and May, this scale is sort of very large. It goes up to 40,000. And it looks like down here, it looks like very, very little was happening. And basically you can't see the change that's going on there because of the scale of the graph. 10,000 is there, so 1,000 is about there. So 1,000 deaths is barely visible on this graph. If we look at the log graph, we're plotting it in a different way so that each tenfold change is given equal weighting, and what we can see is that there is a nice straight, well, not particularly nice, but there is a straight line increase in cases all the way through March and April. So in this period here where the graph is curving up, on the linear graph, here it's showing a straight line, and this is allowing us to see the doubling rate of the pandemic in terms of deaths. So linear graphs are really easy to interpret if you've got numbers that are in a relatively small range. If you've got numbers over several orders of magnitude, and this is one order of magnitude from 1 to 10, and from 10 to 100 another order of magnitude, if data spans several orders of magnitude, or even just a couple of orders of magnitude, often a log graph is much easier to see how the data is changing than a linear graph. Now, one of the most important things to understand in a pandemic is what is the doubling time of cases. So how long does it take for cases to double? Typically, how many days is that? And for the pandemic early on in March, we were looking at around 3 days. And this is a relatively crude calculation that I did. Now I was following cases all the way through March and even before March, trying to calculate the doubling time, and I was drawing my own graphs and trying to figure all of this out. And I came to the conclusion early on in March, well before lockdown was announced or even talked about, that the doubling time was likely to be about 3 days, maybe a little bit shorter than 3 days. And this is how I worked it out. So on the 6th of March there were a total of 144 recorded cases. On the day after there was an extra 55, on the day after that an extra 68, and so on. So we can get a total cumulative recorded cases series going like this, and once you've got about 7 days of data, you've got enough data to start doing a crude calculation. So what I did with this data is I looked at different possibilities, looked at how these case numbers could be achieved by multiplying the case numbers on the 6th of March by a number and then repeat that process. So 144, I multiply it by 1.25 to give 180, which is my prediction there, not far off. Then multiplied 180 by 1.25 to get 225, not far off, and repeated the process. And by day 6, we're still not very far off. Day 7 it was starting to drift out a little bit. But this has told me that the doubling time was a little bit shorter than every 3 days. Now if the maths is troubling you, don't worry, you'll never be examined on this type of maths. It's there for interest really. And basically the calculation that I'm doing is saying that if the numbers double every day, I can say that's 2 to the power of 1. 2 to the power of 1 equals 2. Just in a way that 2 to the power of 2 equals 4, 2 to the power of 1 equals 2. It's just one of those mathematical things you have to accept. 2 to the power of 1 over 2, or 2 to the power of 0.5, equals 1.41. So if the pandemic was doubling every 2 days, we just multiply the numbers by 1.41 every day and then get the resulting number and then multiply that by 1.41. And something that doubles every day rises incredibly fast. I found that the number was about 1.25. If it doubles every 3 days, the number 2 to the power of 1 over 3 equals 1.259. That means it doubles every 3 days, and then 2 to the power of 0.25 doubles every 4 days. So once you've got about 7 days of data, you can do this calculation. And I remember doing this calculation with my students last year and telling them at what date in the pandemic we would hit 30,000 cases. And we hit 30,000 cases within 2 days of my predicted value using this very, very simple calculation. Now the epidemiologists do far more complicated calculations, but this is almost like a rough back of the envelope calculation to illustrate how pandemics get going. So what I'm going to remind you of is just what situation we were in pre-lockdown. So in that week, 16th to the 22nd of March, this was when some people were talking about a possible lockdown, and Spain and Italy were going into lockdown. So on the 16th of March there were just 137 new cases and 22 deaths reported on that day, with a total of 1,400 cases so far. So we're dealing with small numbers, and only 64 deaths so far, bearing in mind that yesterday, which was the 8th of October, there were 70 odd deaths on that one day alone. But we're still dealing with, at that point, very small numbers, but small numbers that were starting to rise in an exponential, predictable way. On the 16th, pubs were still open for the rest of that week, but they were encouraged not to be open. Universities closed, so we stopped our teaching on the 16th or 17th and effectively shut everything down and sent everybody home, but schools were still open right up until the end of that week. So that seems like quite a bold thing to do, given that there were only 137 cases on that particular day, but by that point there were a couple of weeks of strong data telling us the doubling time, and the epidemiologists knew that doubling time was under 3 days on the 16th of March, and that was only going to continue throughout March and into April unless something was done. On the day of lockdown, which is on the 22nd of March, that was a stay-at-home order, and on that day we now risen to 603 cases per day and over 5,000 cases so far, and that was entirely predictable based upon the previous week's data, and 264 deaths so far. This is the time when all the schools were closed on the Monday the 23rd, all the non-essential businesses closed, and effectively the country completely locked down. But the question is, if we got 600 cases on that day, how many cases were there actually at lockdown when this order was announced? And the whole point of this lecture is for you to understand exactly how many cases we think there were and what the state of the pandemic was. And as we will see, it was probably much more than anybody else thought, and the estimates that were made were at the time ridiculed, but now seem to be, if anything, an underestimate. So we're going to try and answer this question: how many people had COVID-19 at lockdown? And official tests really underestimate this. Only the serious cases that ended up in hospital were tested, and if we're looking at about 5,000 cases a day at the peak, this is a huge underestimate. Now we know this must be an underestimate, because if we're getting 5,000 cases a day and that's resulting in 1,000 deaths per day, which is what we saw in April, well, that doesn't fit with between the 10th and the 15th of August we had 5,000 cases, and those 5,000 cases that were officially reported only resulted in a few dozen deaths in the following 2 weeks. So we know that these numbers here, this 5,000 cases per day at the peak in early April, is a massive underestimate, and we need to find out just how much of an underestimate that was. So we look at data from as many different places as possible and do some back calculations. Now this is the key graph that comes out of that first linked article that I put on my first slide, which I told you all to have a look at and read. And this is someone who's analysed the data from the events in Wuhan and Hubei province. And what it plots is the increase in diagnosed patients in hospital. So these are patients turning up to hospital with clinical COVID-19 disease. What you can then do is back calculate the true new cases based on how long it takes for a person to receive the infection and then present at hospital, and we're dealing with about 12 days lag. Now also on this graph is the point in which cases start exploding. So here we've got January 21st, cases start going on. This is where you can see there's an exponential increase going on here. Now you can't actually see it from the graph because of the scale. If it was a log graph, this would be a perfect straight line. But the numbers were suggesting that we've got a doubling time of 2 to 3 days. This was clearly only going to get worse. So the cases really start shooting up here. You can get a measurable doubling time on that. A couple of days later, you have lockdown. Now the effect of lockdown is that official new infections effectively peak maybe a day after that official lockdown, a couple of days after. Everyone who's got it will be locked in at home. They'll give it to their family members, but they can't give it to anybody else. So lockdown happens here. Numbers maybe creep up a smidgen, and then plateau for a couple of days and then immediately start to decrease very, very rapidly. However, the hospital admissions continue to rise, and it looks like lockdown is doing nothing, because at lockdown cases just rise and rise and rise for another 12 or 13 days. And this is entirely predictable because the time from infection to hospitalization is anywhere from 7 to 18 days, typically around 12 days. So once lockdown happened, you had to start the timer and say, okay, in 12, 13 days, we will find out whether this has been worth it. And indeed, in 13 days, we peaked, and then hospitalization cases tended to drop off. So the key point here is the newly hospitalized cases in orange are a measure of newly symptomatic patients 1 to 2 weeks prior to that in blue. So you become symptomatic, and then a week or two later you end up in hospital. Now the hospitalization cases are measuring new infections up to 3 weeks earlier, and peak deaths will be maybe 3 to 4 weeks, will be representing infections 3 to 4 weeks prior. So this is why when lockdown happens, deaths don't go down as quickly as the politicians would like them to go down. Okay, so this whole data was generated by taking people who turn up in hospital who are symptomatic, asking them when their symptoms started, and then adding on a few days to account for the fact that they would have picked up the infection and then symptoms would have started a few days after that. So a patient who comes into hospital on this date would be classed as a true new infection on this date. So this is why we have such a big lag between the true new infections and patients turning up in hospital. And then subsequently you could draw another set of data points beyond here of when these patients then start to die. So based on the follow-up of these patients, what we now know is that over this period of time, this is patients entering hospital, and this is what we also think is going on at the same time. We've got a whole bunch of pre-symptomatic patients who subsequently become symptomatic, who may or may not end up in hospital, but these are the only ones that the official data are showing. This is the number of hospital admissions in Wuhan, and pretty much that was the number of cases, because in China they were hospitalizing even very mild cases. Anyone who was symptomatic initially was hospitalized. So these are patients that we know about. These are patients that at the time we didn't know about but were infected. And from this data set, we're estimating that only 1 in 17 cases were known about. The vast majority of COVID-infected patients were not known about to the authorities, and that is no different to the UK. So one of the questions we want to answer is how many people have been or currently are infected in the UK. And there are a few things that we need to know to be able to start making these calculations, and then using data from China, using data from other places, and try to come to a logical answer. We know that how many people have been previously infected because we can do antibody tests, and when you're infected with the virus you then generate antibodies to it. So if you're antibody positive, you've been infected. And we think around 30 to 40% of patients in the early studies were showing detectable levels of antibodies. We can look at daily infections in hospitals and testing centres. What we know early on in the pandemic is that this was very heavily skewed towards very severely ill patients. If you turned up at hospital, you got a test and you were COVID positive, whereas if you were not unwell enough to go to hospital, you didn't get a test. Now, testing is skewed towards asymptomatic patients by contact tracing and other reasons. We've got more tests to do, therefore we can test a wider range of people. So we're testing many more people who don't have symptoms, so we're detecting many more people who are not going to get unwell. So we can ask the question, how many are currently infected, by doing viral RNA detection, and we look at the test for that next week. And we estimate that around 78% at the time of being tested are asymptomatic, and a very small minority are hospitalised, and that's across the whole population. Some of these asymptomatics will become symptomatic subsequently, but at the time where they tested, 78% are asymptomatic. And we get a lot of this data from the what I call the ONS survey, the Office for National Statistics COVID Surveillance Survey, which you can follow that link and look for the most recent data on there. I'll be looking at some more of that on a later slide. Now, the other thing that can help us predict how the pandemic is going is how many people are hospitalised and how many people have died. However, this is probably the most reliable data. It's not affected by increases and decreases in screening of asymptomatic people, like the current testing system is. However, the problem is you're looking at the infection rate 3 to 4 weeks ago, and if you let an infection run for 3 to 4 weeks, then you start seeing deaths going up, and then you start to act. You've got potentially 3 to 4 weeks of rapid increase in deaths that you can't do anything about because those infections have already occurred. And this was a major problem with lockdown on the 22nd, 23rd of March. Some of the most reliable estimates suggest that the majority of people who died may well have been infected prior to lockdown, which seems a really quite stark statistic to think about. But when we look back at those graphs, you'll see that that is indeed the case. So to help answer the question of how many people have COVID-19 currently, one of the most reliable places to look is not the figures that come out for daily numbers of cases, because they fluctuate based on whether we're testing a localised area of students or how many tests are processed on that day. If you process double the number of tests, then the number of positive cases may well double. So that fluctuates a lot. There's this study going on, the Office for National Statistics COVID Surveillance Survey. If you follow that link, you'll get to it. And this looks at the random population. So we send out test kits to thousands of people each week. They do self-swabbing, they send them back, and they're all tested. So these are randomly assigned to the population. Now, this is skewed towards people who are well, because if you're unwell with COVID, you're probably in hospital. But so there are some skewing effects going on here. And it's also skewed. I very much doubt many students are currently taking part in the ONS survey because they are in halls of residence. What we found is that through the very first data set in late April was very alarming, but then through May into June, the percent positivity within the population dropped considerably as we got on top of the virus. So in early May, 1 in 400 people were positive at any one time. That's 145,000 positives over the course of that testing period, and that decreased by 5-fold over the next 7 weeks. So we can follow this graph going down. And this is a sort of readout that you get from here. It gives you the number of people in the country, the estimated number of people being positive for each particular time point, and then they can express that as a frequency 1 in 400 in May down to 1 in 2,000 in June, and it dropped a little bit lower than that throughout August. And this is the most recent data set. Is plotted in 2 different ways. One, the absolute values with an error bar. Now the error bar says that basically the data that they've got could fall within that region because there's a small number of people tested, and by random chance it could be there or it could be there. Then there's some mathematical predictions of where we really think it lies based on previous week's data and complex maths. So you end up with these graphs, and these show percent positivity. So 1% positive means 1 in 100 people are positive for it. Here we're looking at 1 in 200 people being positive at the end of April. This dropped to 1 in 2,000 throughout late summer, and now it's back up again, heading towards an average for the country as a whole, well, for England as a whole, sorry, this is just England data, of 1 in 500 currently. And now we've got data on Northern Ireland, Wales and England, and we know the rate in some of those areas is 1 in 200 and 1 in 300. Now compare that Office for National Statistics data with what is reported formally by the government, and for example at the end of August the daily number was about 1,300 cases per day. However, the Office for National Statistics survey was suggesting 29,000 new infections a week, or 4,000 new infections per day. And what this is telling us is all of the testing centres are picking up people who identify as either having symptoms or being in close contact with someone with symptoms, and that's picking up a third of all of the cases that are out there. So there's another 2,600 cases on this particular day who have not gone to a COVID test centre to get a test. So the official figures are also, not only they're massively underestimating here, all the way along here, by doing random sampling of the population to find out the rate in the population, we're finding that this graph should probably be about 3 times higher. And most of the data sets, it's been in anywhere from 3-fold to 5-fold underestimate of the true number of cases in the country at any one time. Now this is what the data looks like now. There we are, 5,000 cases a day in April, dropping down to about 400, 500 cases a day throughout parts of July and parts of August, and then we've got this rapid rise here. And what we can start doing now is doing calculations on the doubling time of the infection. And what's clear is that this is going up much more slowly than it did down here. That's not entirely obvious from the graphs, but that is what's happening. Whereas here we've got a doubling time of maybe 3 days, 4 days at some points. We might be talking about a doubling time of a week to maybe even 2 weeks at the moment. And just for a rough ballpark, if you draw a line sort of down there, you could say, okay, we've hit 15,000 there, we've hit 7,500 there, we've hit 3,700 there, and those are about, depending on the fluctuations, about 10 days apart. So that we're looking at a doubling time of anywhere between 1 and 2 weeks currently. Probably 1 week is a bit pessimistic. Now there are lots of other ways in which the data can be misleading and make it difficult to work out what's going on in a pandemic. So from the UK, the official reported figures are we hit a maximum of 5,000 cases per day, and we hit a maximum of 1,000 deaths per day, and the deaths have followed a lag of a couple of weeks from the cases, but that would suggest a 20% case fatality rate, saying that 1 in 5 people infected die. Well, that's clearly not true. We know that that's not true. It just means that 1 in 5 of people who ended up in hospital and were classed as a case in late March and throughout April, about 1 in 5 of those died, and they were the really serious cases. We know data from the Diamond, the Ruby Princess cruise ships. There were 37 deaths out of 7,500 people. Many of those people on the cruise ships were quite old, but most of the crew were quite young. Even with that mix of, probably, quite an elderly population, but maybe relatively fit old people, you're still looking at a fatality rate of 0.5%, very different from 20% here. So official figures aren't necessarily what you think they are unless you actually interrogate the data. Early estimates from China and elsewhere suggested that the death rate was 1.3%. It's difficult to know whether that is a infection fatality rate or a case fatality rate. Remember, a case fatality rate or ratio is a case that turns up in hospital with clinical disease, but whereas an infection fatality ratio is an infected person, and that could be a young, fit, healthy student who's not going to die from this. So infection and case fatality rates are different, and right at the very end I've got a bit more on that. However, if you do some clever maths based on all of these data points that I've talked about, we're looking at 1,000 deaths per day. If we're looking at a death rate of 1.3%, those 1,000 deaths per day would come from 77,000 cases per day in March and April. So if this is a case fatality rate, we could multiply up to find that you would need 77,000 cases per day to get 1,000 deaths per day. During this period, about 5,000 per day were reported. So this is the point I'm getting at. The data in April does not reflect the true situation. Now, to get from here to here, you can multiply up by about 17 or by 15, sorry. The Wuhan data suggested it was 1 in 17 cases were being reported. Here, a rough ballpark figure is 1 in 15. So these are not far apart. So this is suggesting in the UK, around about 80,000 cases per day might have happened throughout March and April. And we can use some of the Office for National Statistics data to do something similar and come to a very similar conclusion. So we can look at the first set of ONS data that was published in April and early May. We can look at the hospitalizations and subsequent deaths that occurred in the following 3 weeks. And what we know is we've got 145,000 cases per week, 1 in 400 of the population were infected. By mid-May, we're looking at that. This isn't in a week, so this is equating to 21,000 new infections per day. Early June, 250 people per day died, so we're looking at about a 1.3% fatality rate, which matches figures elsewhere. However, this is probably an overestimate. These are relatively crude calculations, but they give you a rough ballpark figure of what is likely to be going on. If you work on this sort of figure, work on these particular figures, you end up with a 1.3% fatality. So everything I've been talking about so far has been testing for presence of the virus in patients who are actively infected at any one time. And there's another thing that we can do is then look back in time and ask the question, has a person previously been infected with the virus? Have they generated antibodies? And a few big studies have been performed to look for antibodies in patients in the UK to find out how many people have had the infection. Now what we do know is by the end of June, 3.4 million people had been infected. Now if you know by the end of June how many people have been infected, well, this averages 35,000 per day over the entire period of March, April, May, June. And we know that there was a huge peak in March, so it's likely from this data alone that we're looking at over 100,000 infections per day throughout late March. And if we're now upping our estimates of how many people were infected per day, then the infection fatality rate starts to decrease. Factor in that some people don't produce a good antibody response, this number can be even higher. All of this data is pointing to an infection fatality rate of less than 1%, which fits in with lots of other studies that have done something similar. And these are various studies that have shown infection fatality rates 0.91, 0.7%, and plots that data based on age. And you can see that over 75's infection fatality rate of 11.6%. So now we've got a lot more data, we can now start drawing graphs like this, which show cases, and it's saying there cases in inverted commas because these are not necessarily cases, these are now infections. So here, these are true cases. Then as we start to ramp up screening, what is classed here as cases are actually just infections. Not all of those are cases of COVID disease. Most of these are asymptomatic cases. So this means that you can see a graph that goes up, down, and then goes up again. And when we get to this point, well, that's the same as here, but this does not reflect the same position that we were in April, nowhere near. And you can see that deaths on this particular graph have just started to uptick a little bit down there, but we're not seeing a substantial death rate. You know, we're not seeing this go up here because most of the people who are being picked up here as cases in inverted commas are not cases of COVID-19 disease. They're just infections with the virus, largely very mildly symptomatic or asymptomatic. Now, it's misinterpretation of this sort of graph that has made some people in the general population think that the disease has gone away, that look, we're up to the same level as before and surely we should be seeing lots of deaths, but that is just blatantly wrong. But unfortunately that has resulted in a lot of people no longer fearing this disease at all. So we can now answer what March to June 2020 might have actually have looked like on it in terms of cases and deaths and official cases and asymptomatic cases and so on. So I've done a lot of calculations combining deaths, fatality rate, deaths versus community infection, antibody positivity, and all of my calculations come to a value of 75 to 130,000 cases per day at the peak. And other people have come to a similar conclusion. This is somebody else's analysis of the data. This is my analysis of the data. I can't be sure whether that's 75 or 130,000. But what we know is numbers in April were at least 17 to 20-fold underestimate, possibly much, much more. What we also know is during the end of August, we increased from 500 to 1,300 cases, and that doesn't reflect the same change of 500 to 1,300 cases that we observed around about lockdown from 21st of March to 26th of March. We had 500 increasing to 1,300. They are completely non-comparable. Now, all the calculations I've been talking about, I've done on the back of an envelope based on publicly available data. What other people have done is using slightly better computer models and so on, and this is a group from Imperial down in London who have calculated that at the peak, at lockdown day, there were somewhere in the region of 320 to 340,000 cases, infections, I should say. Immediately that dropped, and then we ended up with over the next few days around 130, 150,000, which is sort of the numbers that I'd calculated, and then that drops off. So this is the set of data now that suggests, and this was only published very, very recently, suggests that we spiked up. We're at this sort of level. If we had let this infection run for another 2 days, we could have doubled the death rate. And that is what happens with exponentially increasing epidemics like this. You have to decide that there was a point where this had to be stopped, and that was lockdown. One more day, deaths may well have increased by 50%. So we now found ourselves in a position of a second wave happening, and the second wave, this illustrates what's happening with the second wave throughout June, July into August. Case rates were low. This is cases per 100,000. They were low across the country. But what we start to see initially in the 20 to 29-year-old group, and then feeding into the 30-year-old group, an increase in cases going up quite substantially, bearing in mind the pubs opened around about here. And there was the Eat Out to Help Out, and there were lots of young people going out, potentially infecting each other and meeting up. So this is where it all started. At this point, we've not yet had the virus entering the older high-risk age groups, but what you can see is the frequency of infections starts here and it radiates up here and it sort of heads down here as well. It doesn't really affect the school-age kids at this point, really. So that's what's going on in the UK. So that was the UK situation, and we've got similar data sets from countries all over the world showing different week numbers, and showing that the infection here in Spain starts off in the young people, and then the week after migrates to the older people, and then it sort of works its way up into the very old population. So they're now starting to see quite a high number of deaths because the infection has spilled over from the young people in the bars and the restaurants through to the older people in the care homes and hospitals. And we saw something very, very similar in Florida when their students went back, and we had a real issue of effectively their Freshers Week type parties going on, and you can see the infection stems from the younger age groups, becomes very, very prevalent, and then spreads up through the older age groups. So this is something that we'd seen happen in lots of other countries before. Now the question is, what's going to happen in the UK? Are we going to get this infection spilling up into the 80-plus-year-olds, because we know that they are at very high risk of death? And if you want to know how much of a high risk of death, well, it was present on one of the earlier slides where there was a infection fatality rate of about 11% for the over 75s. This graph shows something different. This shows how much more deadly an infection of COVID-19 SARS-CoV-2 is compared to influenza across many, many different years. So this is seasonal influenza in America, lots of years of data, and what you can see is the infection fatality ratio of the 80-year-olds gives you a number. That's a percent of people who would die from catching influenza. You know, about certainly less than certainly more than 1 in 1,000, maybe 1 in 500-ish. What you can see is if these people catch SARS-CoV-2, they are 13 times more likely to die from this than they are if they're going to catch a regular seasonal influenza. And what you can see from this data is in the over 70s, and in fact from this this is only comparing to influenza, you can see that in the 60s, 70s and 80s, this disease is 13 to 14 times more deadly if you catch it than influenza. And then you find that the younger people, there is a zero increase. Basically, if a young person under 25 catches this particular infection, their chances of death are A, very small, and B, no different to if they caught regular influenza. Whereas when you get to someone of my age, we're starting to get to the age where this disease, COVID-19, is substantially more deadly than influenza, and that gap widens with increasing age. So you hear some people saying it's just like regular flu. It's not regular flu for most people. It might be for you in terms of chances of dying from it, but for everybody else it is not regular flu. So I've given you an awful lot of definitions, an awful lot of different ways of calculating this type of data, because in your coursework I want you to use at least one of the sorts of data that I've just described here, whether it's infection fatality ratios, case fatality ratios, correlating deaths with case numbers, maybe doing a case study on the Ruby Princess cruise ship, something that involves some applying of numbers to this pandemic, and a written report is what I'm going to be asking you to do for your coursework. So the reason I've given you all of this, not so I can test you on your knowledge of all of these things on an exam, it's groundwork for you to understand and think, okay, I can take one element of this forward and do a piece of coursework by exploring it in more detail. So that's what I want you to do. And there's a little practice for that. What we're going to talk about in the tutorial, as well as helping to define anything that I've talked about in this lecture, is look at the following two graphs and imagine you've got to explain this to either a non-scientist or a COVID-19 denialist elderly relative. Okay, the sorts of person who thinks death rates are not going up but cases are higher than before, this virus has lost its potency. So I want you to be able to be in a position to explain this concept and dispel myths based on hard scientific evidence. So we're going to be discussing that type of thing in the tutorial, as well as anything in this data that I've described today that you found problematic. And these are the two graphs that we can look at. But you look at them in more detail and we'll talk about those during the session on Wednesday. Okay, that's all from me. Sorry it took so long.